Okay. All right, today's lesson, kind of in general, Unit 1 is a little like disconnected with the things we've learned. Like you could probably stretch and find a connection, but other units have much more like flow. This one's kind of like, hey, we're learning about this. Okay, now we're going to learn about this, and besides chemistry, it feels a little random. So today's doesn't really have anything to do with what we've been talking about besides the fact that it's about an atom. Okay? Today our discussion and our learning is all about, oh, let me zoom this big, electrons. So that is the highlight of today is understanding about electrons. Now, the reason why we care is that electrons determine the reactivity of atoms. Why things react or why they don't react is because of what the electrons are doing, which is pretty much the basis of the entire class of chemical reactions. So I have a little demo just to get your brains going and once again to connect the three sides of our chemistry triangle. Where's my yards? Okay, but what I want to point out is that our objective today is being able to write and understand what are called electron configurations. Okay, maybe it won't make any sense right now, but by the end, that's the goal we're looking for. Do you need a note for your teacher? Sure. No, you're okay. If I can find a piece of paper. Found something. Thank you, though. So I use real paper like I am. Yeah. No, you only got one because when I still have to grade. Yeah. So that's good. And if you want all your homework.
Just watch the same segment of her just smiling over and over again.
Well, you get an
Unlimited smiley glitch. We found the loophole. No.
There was one.
There was.
Really?
I just don't pay attention enough.
I was doing homework last time.
That's why you don't get any boys. Dang it, I should have brought my coffee John today last night.
Electron.
Drive home.
Yep.
Come back.
Okay, so with our chemistry triangle, with what we're learning today, it's very easy because it is heavy on this side. We are heavy on, we're writing these symbolic formulas out, okay? But even though like this is the focus, you don't want to only be there and not understand like what it represents, what it means, so on and so forth, okay? So I have two flasks up here. They're known as volumetric flasks, or their name. In this first one, I'm going to pour some distilled water.
That's some distilled water.
Is it edible?
Is distilled water edible?
That's what Ethan said.
I don't know, I'd say edible, but drinkable. Yeah.
Consumable?
Yeah. Okay, in the second flask, I'm going to put some hydrogen peroxide. Okay? Now, hydrogen peroxide, you may have it at your home. It's normally in a rectangular brown bottle.
No longer drinkable.
Yeah, this is not drinkable.
I mean, you can drink it, just it won't go very well.
That's true, I guess. Dye? I mean, the one at your house, maybe, because it's only, so this is a 30% solution. The one at your house is only a 3% solution.
Oh wow. I'll
But
take
yes,
one for the
it would
team.
corrode your, like, throat as it goes through.
Oh no.
And then also,
Alcohol. I bet so.
yeah. You'd have to call police and insurance, and then they'd probably be like, why did you drink that?
I was a little thirsty. I thought it was fruit
Okay, so, two different substances, okay? I'm gonna add the same thing to both, to just once again show the idea of like, some things react, some things don't, and at the molecular level, it's all about their electrons. That there's something about their electrons that's causing them to do something or not do something, okay? So I'm adding, it's called manganese dioxide. It's a very fine black powder. Okay, so I'm just gonna add a little salt to our water. Observe what happens.
Wow.
Dark.
Yes.
Add some to our.
Oh! It's a bomb!
I guess
It's a cloud. So once again, two totally different results, right? Once again, in this one, the electrons are changing, right? They're trading, they're sharing, something's going on that's causing the Legos to rearrange. In this one, the Legos are just mixed. It's a mixture, but there's no unstacking or restacking of the Lego combinations, okay?
If
Person.
you read that in, will you die? That's what I was
Yeah, that's why I sent it to the vent
Well,
of the
but there's
school.
still some that escape. We're gonna die.
It's literally a cloud. It was water vapor and oxygen gas.
Oh, okay. Awesome. We're not gonna die.
Yeah, I just sent dangerous fumes into the school.
Just like, oh, okay.
Good for you.
Good luck. We're in the gas chamber now.
Okay, so our goal is to write this theme known as an electron configuration. You can think of it, some people say it's like an address for all the electrons. Okay, so if something has 50 electrons, the electron configuration will tell you all the locations of all 50 of them. Okay, now, I have this model here, mostly to talk about how wrong it is. Okay, this model does not do the electrons justice of what's really going on. But the reason why we use them is it is a good starting point. And to model what it really is quite complicated. You have to model it in like this tangible kind of way. But keep that in mind, okay? So I'm going to show you kind of your success criteria of the end goal. Okay, in the end, so this will make not much sense now, but keep in mind this is where we're going. You should be able to say, if I said, what's carbon's electron configuration? You would say 1s2, 2s2, 2p2. And that's how you read it. Okay, you don't read them as squared. This is not a mathematical operation. So you just say the number as it is. Okay? The other thing is a visual representation of this. These two give me the same information, just in different ways. Okay? So in these boxes, you're going to draw some half arrows. In this first one, we have one up and one down. That's what I mean by a half arrow, is it doesn't have another side to the, I don't know what you call it, top. Okay? In this one, we have 1, 2. And then in this last one, we have one in this box and one in that box, each with the same direction of that they're going.
But why?
So, once again, in today's lesson, here's I guess my other disclaimer. The first part's going to feel a little bit haphazard in the sense of like, I'm giving you puzzle pieces, but like that's the end goal, but it's hard to see it. So just stay with me, I promise. Okay, one of B6, just as they were leaving, we're like, that made a lot of sense. Like, I have faith that will make sense for you guys too. But in the beginning, if it feels a little like, what is going on here? Because we're going to talk about bunk beds, like, stay with me, okay? Exactly.
I had a bunk bed.
Okay, who doesn't want a bunk bed? Okay, so with this idea of the electrons, I've come up with an analogy I've used to help teach this. Okay, with this analogy, once again, it's just to help bring something that's really, really abstract to maybe something a little bit more tangible and understanding, even though obviously there's flaws in it. Okay, so keep in mind, our goal is that if I have carbon, carbon has 6 electrons. And remember, the proton number is the electron number that's not charged. Okay, we want to designate where those 6 electrons are going to check in to our hotel. Okay, so the first thing we do when an electron checks in is we tell them what floor of the hotel they're going to go to. Okay, in terms of the actual atom, these are the energy levels. The energy levels are like floors of the hotel. In terms of, so I wrote over here, this is the carbon example you guys already wrote down. I'm just going to reference it, so I put it here as well. Okay. In terms of an actual configuration, The hotel floors are represented by the number in front. So when I see 1S2, 2S2, 2P2, these that I'm circling in blue, this represents the energy levels. Okay, so the large numbers in front represent the energy levels. The possible values that can exist for energy levels range from 1 to infinity.
Wow.
As of right now, scientists have not claimed, like, oh, that's the biggest hotel that it can
Hotel
be.
floor.
Now, in terms of what we've created in atoms, there is like a limit. The biggest atoms we've made go up to 7 energy levels. But scientists aren't saying like it can't go to 8 or 9 or 10 one day, okay? Okay, questions on our energy levels. Okay, so little electron comes in. I need to check into my room. You tell them what floor to go to. You then tell them what room to go to. Okay, the rooms in the actual atom are known as sub-levels. So once again, this is where this model fails because it only shows energy levels. It doesn't show anything past, which we're going to look at. There's like 3 layers deep. Okay, but this model stops at each of these rings would be like an energy level. But in actuality, inside those rings are sub-levels. Okay, scientists have chosen to designate these by letters. So they said, let's use numbers for energy levels, we'll use letters for sub-levels. There's 4 different types of sub-levels that exist. So in the configuration that S, so when I have 1S2, the S is signifying the sub-level. Which once again would be like the room on the floor. Now there's 4 main types of sublevels that exist. Once again, now, who knows, down the road, maybe they find another one and give it a letter. Okay, so there's S, P, D, and F. Are the different types of rooms in the hotel. Okay, so some electrons could be in an S room, some could be in a P room, some could be a D room, or some could be an F room. There is a reason to the letters of like, why not A, B, C, D? But we're not going to talk about it right now. But, okay? Okay, so we tell them, okay.
How do you find the letter if it's not on the periodic table? Or is it on the periodic
It is. It's just not as obvious as the room number, or the energy level. But there are sections that signify the different areas, which we'll color in a moment. Yeah, good question though. Have a smiley face for that. Okay, so electron comes. This is a very specific hotel if you're not, by the way. So that you're going to tell them you're on this floor, you're in this room, inside the rooms, this is a bunk bed only hotel, and you're going to tell them exactly what bunk bed to sleep in. Okay? So the bunk beds are inside the sublevels that are inside the energy levels. Okay? And these are called orbitals. Okay? So the orbitals are like bunk beds in the room. Now, in terms of this notation, the orbitals are somewhat hidden in like it's not, like this is very clear that S is the sublevel. The orbitals are within the letter because each letter has the same number of orbitals every time. So I'm going to come over here and then we'll come back to this one. So an S room only ever has 1 bunk bed. It doesn't matter if it's on the 1st floor or the 7th floor. If it's an S sublevel, it only ever has 1 orbital, which is represented by a single box. So that's where we can see it is in the visual representation. Notice that the 1s is 1 orbital. The 2s is 1 orbital because they're both s's. 3s, 1 orbital. Okay? All right, the p has 3 bunk beds or 3 orbitals. The way we represent that is by drawing the 3 boxes all connected. That says, hey, these 3 bunk beds are in the same room. There's just 3 bunk beds. Okay? The D folds up to 5, has 5 orbitals. So you draw 5 boxes all connected. And then F, any guesses?
7.
Yeah, you see the pattern? 1, 3, 5, 7. Atoms have so many patterns.
Can they ever go above F?
As of right now, no. Like the biggest atoms don't go past F, but once again, if they make bigger atoms, then they might have to figure out what that next orbital would be, which would most likely would be 9, right? But yeah, great question though, Ephraim. Okay. Got it? So, energy levels, sublevels, orbitals in the sublevels, and then the reason why I picked bunk beds for my analogy is because one electron has to sleep on the top and one has to sleep on the bottom, which correlates to the electron spin.
The what?
The electron spin.
Is the line next to the E signifying anything?
Yeah, it's like this is like like a shortcut to say electron because it's E negative. So electron negative. Sorry, it's like a symbol, there's the word. So, okay.
That's smart.
This is signified by, so in the 1s2, okay, I'm going to draw it 2 ways. So we had that, and then in this, it's signified by the up and down arrows, which should match the exponent, or superscript. There was 1s2, which means there should only be 2 arrows in that orbital, but they should always be pointed in opposite directions. Yeah, Lily.
So if you just had well, doesn't exist, it's just like a 1s1, I guess. That like it doesn't have one on both, and if so, does it matter which direction the arrows point?
No. Yeah, great question. The key thing is they just have to go opposite ways, but whether it takes the top bunk first or the bottom one doesn't really matter, and we don't really often know. So yeah, good question though. Have some answers to that. Yeah, Christina.
How come for 2p2, it's not in the same box for every single?
Good observation. So she noticed that we have 3 bunk beds. We only had 2 electrons that we needed to place. So that's why it's not like completely filled, and the way we placed them was 1 here and 1 there. So the next thing we're going to get to are their rules for the hotel. There's the rules that the atom always follow. I guess you'd almost say patterns that we've discovered, right? That the atom always does this, and that falls in one of the rules we're going to talk about just barely. So great question, okay? With that, I just want to say this, and then we'll go on to the rules, okay? With this lesson and others in general, sometimes it's helpful to keep in mind that scientists didn't make the atom. We've made some atoms, but like we didn't build the atom. Atoms have been here from the beginning of time. We just are trying to understand them, and that's what all these weird labels are. Is us understanding like, okay, we know that this is there, we know that this exists, so let's call it the 1s, so on and so forth. But why is it 1, 3, 5, 7? I don't know, it's just how atoms are made. And other things like that. So kind of keep that in mind if you're having a little bit of like, well, why is it that way? It is one of those things where it's just, atoms are built this way, and we're just trying to find the patterns to them, okay? All right, so the 3 rules of our hotel, okay, is we have Pauli's exclusion principle. He was the one to discover that an orbital, aka the bunk bed, can only hold 2 electrons. Okay, it can only hold 2 electrons with opposite spin. Now, in case you're wondering, it's not really that important. Like, you don't have to memorize the name of a rule. It's like the AP test will never ask you, like, what's Pauli's, like, who came up with this principle? They'll never ask you that. We just want to give him credit. But, like, don't add that to your, like, oh, I have to memorize these names. None of that, okay? So the idea of this, once again, is it can hold 2 electrons, but they must have opposite spins. So, if I have the 1s orbital, right, that's why 1 goes up and 1 goes down. If you want to go down then up, you're still following the rule. But you would never have a case where they're both spinning up. It doesn't happen, ever. Okay? Now, in case you're unsure, what we mean by spin is so, it's like the Earth, right? The Earth orbits the sun, but at the same time as orbiting, the Earth is rotating, and that's what electrons do too. Is they're orbiting, but they're also spinning individually, okay? Okay, questions on Pauli's rule, exclusion principle? Okay, the second principle or rule of our hotel is Aufbau's principle. He's the one who discovered there's a pattern, okay? That whether I have 10 electrons or 50 electrons, we're always gonna fill the rooms in the same order every single time. And that's what makes this hopefully come all together. Okay, it always fills from the lowest energy orbitals and then goes up. So the first electron will always go in the 1s every time. That's the lowest in energy. Now, we're going to be using the periodic table because there's a really cool pattern or connection between this and the periodic table. It's kind of actually quite miraculous because the periodic table was structured before this was known. And then they're like, oh my gosh, it matches just because of how atoms work. But in order to do that, you have to look at the periodic table in its true form, meaning put them in number order, okay? So look over here with me, okay? So everything stays in number order up to 56. If I read left to right, goes 1, 2, 3, 4, so on and so forth, up to here. But at this point, some weirdness happens in that they have taken 57 through 71 and cut and pasted them down here. On mine, these are just spacer blocks. This isn't an element. It's just saying, hey, these ones are down here, these ones are down here. So they cut them out, pasted them down here, because then notice it picks up at 72. So when we look at the periodic table, this is what it actually would look like. If you put that section back in here, this is where it fits. Does everyone see that? So kind of cut, push it over, insert it back up, and that would be the periodic table by number order. Now I've yet to find actually a good, a good reason of why we don't just use the periodic table like this. Besides, it is nice on a piece of paper, but that's what it is. Okay. All right. We'll come back to his rule here in a second. Yeah, definitely.
Would that mean that the 71 and 103 actually belong in the D block?
They do. So that one, great observation. It totally depends on the periodic table and how they made it. The ones on your laminated ones are one of my favorite, where they put a spacer block, but they actually leave a space. On mine, they took the place of an element, which you're totally right is that LU and LR right there at the end. And so it makes it a little deceiving of that F and the D. So yeah, great observation. So that's why these ones are on the tables, or these are my favorite in that it left that space, which helps you better visualize where. I don't know what your AP one looks like. Does it have a space? Does it have that handy? No, does it do it like this one? Yeah, that's one, I don't like it that way. Yeah, Levi.
So with the, up there, it
Yeah.
said that the F ones were 4 and 5, but on these it says that, why are they not 6 and 7 with the rest? It's
Great observation, and we'll get to that. In that these numbers, this will be my answer for now, but then we'll answer it more. These numbers, the 1, 2, 3, 4, 5, 6, 7 here, don't hold true for all of them. And so, yeah, that's why the F and the D you'll see don't quite follow that pattern. It helps for some, but not for all of them. Okay? All right. Zach, we have a smiley face, by the way, for that. Coming face, and Levi as well. Okay, the last rule is Hund's rule. Okay, this one will go with what Christina brought up of why did we do this? So what he discovered that when you have electrons and they're not in a full, it's not completely filled. Okay, let's say for example we had 4 electrons. Okay, now this one could hold up to 6. Okay, but there's only 4. Good luck, girls. Okay, so the way that they go is if they can have their own bunk, they're gonna take their own bunk. So 1, 2, 3. Since I'm doing a 4 electron example, somebody has to share. You can't just like leave out an electron. But if they can have their own space, they take their own space. Which is why here we did this versus pairing them up. Okay? It's just like humans, right? You have 3 people and you're in a room with 3 beds, you're all gonna take your own bed. Right? Most likely. Okay? So an example that wouldn't happen is like we wouldn't see that. Right? Like you're never gonna have an empty room, empty bunk bed if there's room to spread. Okay? The other part to this rule, we're gonna draw another bad example here.
Sure.
Okay? The other key component is this idea of parallel spinning. Okay? When they're spread out and not paired up yet, they're going to spin in the same direction. Hence why it went up, up. Okay? So like if you only had 3, they're not going to go up, down, up. That's what it means by parallel spin, is if they're spinning up, they're all going to spin up, or they're all going to spin down. So this would never happen as well. Yeah?
So is it like possible, like for the first example, could you go like down, 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 and then add one that goes up? And then
Totally. Yep. Yeah, if you choose to start down and then go up, that's fine. Yeah. Good observation, Alan. Other questions? Okay. We're gonna take a quick coloring break, everybody. Turn the page.
Oh, thank heavens. Hallelujah.
Okay, turn the page and there's a blank periodic table. You need to pick 4 colors. Okay? 4 colors.
I hate my life.
Okay, and you're gonna color. It's blank on purpose, by the way, so don't add an element. Okay, we want to look at this as a blank map.
Yeah.
Okay, but pick 4 colors, and you need to color in and label as their section. So the first 2 columns. Now don't mess this one up. Eyes up here really quick, because everyone messes this up. So the first 2 columns plus this little square over here all need to be the same color. Okay, and that is known as the S block. Okay, so red for me is the S block. Okay, so the first 2 columns, that's your S. Now, we have other things to do besides colors. So those of you that are like going square by square, maybe pick up the pace a little bit. Just shade it out. So you need S, P, D, F, label the color, shade in the area, and then once you get it shaded in, you'll also add the numbers and arrows that I have. So yours should look just like mine, except with the colors of your choice. Okay? I'll hang you back up here so those on the edges can see better. Do you see that okay? So I can zoom the lines.
Yes.
I can't tell what the charisma color.
Oh, yeah.
Whoa. Now my purple is neon.
Yeah, good.
I can't tell D and F apart.
You're good. So D is like that lower middle section. So like from here to here, where it's lower. So F is just this bottom part. Yeah. So shade in the different colors.
This blue and purple. See why you put that thing on? I almost just died. My life flashed.
Live flash before your
Wait,
eyes.
so 5 and 6 are actually 4 and 5?
Yes, so that's where Levi noticed on our other one, the numbering gets a little weird in the D and the F section. It doesn't line up with where like the other ones do.
don't need a number line?
Oh, this is so.
We do?
Yeah. Oh, and. Wait, so why is it, what?
Don't question it.
I'm questioning it very hard right now.
You can question it.
Okay, so why does the blue start with 3, but then with the orange to the left of it, it's 4?
Good question. I'm not gonna answer it right now, but we will answer it right.
I'm so confused.
Just write it down for now, and then once we get all the pieces there,
Okay.
we will answer. Because that actually drove me insane for the first 2 years of my chemistry study. Because I couldn't get a good answer. So hopefully I can give you an okay answer. I won't say it's great,
Wait, the
but.
line number is what?
I want an amazing answer. Just kidding. Okay. As long as you give me a respectable good answer, I'll be happy. Wait, what?
I didn't see that you're trying to make it. I didn't even put one of those.
Why is the pie there? I was like, 4. This is obviously dead. Alex. You're gonna hear that on the camera. On the
He's
recording.
not gonna watch the whole recording back.
Yeah, that's true.
Unless if he does.
Every level psychotic. No offense, Mrs. Officer.
Where did she go?
We love you, Mrs. Officer.
Take a pose. Come on.
It's just a
This is a serious matter.
I'll pull our phones out and see this all. She can't got all our points. She can't see us all. She only sees.
Okay, are we ready?
Yeah.
We have the beautiful map made. Okay, let's take a look now at how to use our map and put all of this crazy stuff together. Okay, so this is now the point where, like, hopefully you all have that, like, moment of, like, I get what you're saying and everything. Okay? Okay, I'm gonna actually help those that are gone. Use this. Hold on a second. I'm gonna make it slightly smaller.
Yippee.
Okay. It has time for that. Okay, so goal here is using our map and what we've talked about, write out electron configurations and orbital diagrams for any element that I give you. Okay, so the first one, we're gonna go through that chart right there. I'm just leaving this up here, so you can look at it as I would look at your map. Okay, so here's my map. You have yours colored according to your sections, right? Okay, so our goal first off is we're doing hydrogen. Okay, so the first step is finding hydrogen on the periodic table to know how many electrons are in its hotel. So hydrogen has one electron.
Uno.
Okay, very simple. Big hotel, but only one electron lives there. Okay. I like to do the configuration first. I should have switched my table. So I'm going to do the configuration and then the orbital diagram. That's the box part of it. Okay. So first thing I do is I put my finger, or I put a mark on the thing I'm trying to write the configuration for. Obviously this one's the simplest, but building a pattern here. This is where I'm trying to go in the end. Okay, put my little magnet here. You always start from that spot, no matter what, because you have to go left to right, down, left to right, down, left to right. Okay, so what energy and sublevel is represented by this on your map? 1s. Because notice, it's in the S section, and it's the first one, so 1s. So I'm going to write, for my configuration, 1s. How many electrons do I need to put in that room?
One.
Why only one? Because I only have one. And now we're done. Because as soon as I've gotten to the square I need to, we stop. Okay? The orbital diagram would be represented by a single box, labeled as 1s with one arrow in it, pointing up or down your choice.
Can I point sideways?
Cannot go sideways.
Dang it.
Yeah. Only says no.
What if I turn the paper 90 degrees?
Okay, lithium. Okay, so find lithium on the periodic table.
Where is it? Oh, right there.
Right there.
Got it.
Okay,
I cannot.
so I put my magnet there. Now, you gotta start at the lowest and build up.
Wow.
So this is always the starting point. You wanna put that on your map, you have to start here every time. Alright, it's like the start of Monopoly, that's the start spot. Is there start? Yeah. Okay, alright, what orbital is represented by this?
Why?
1s. So I write 1s. Now this time I'm trying to get to here, so I'm gonna fill up the 1s with 1, 2, because that's the max it can hold, electrons. Now I've gotten to this square, it's full, so now I have to move over here. So what orbital is represented here? 2s.
Okay.
How many electrons do I want to put in there? Just one, because my marker's on the first one. And your exponents should always add up. So write that down to the total number of electrons. Alright, 2 plus 1 is 2. In modeling it, I'd have 1s, 2s. Don't connect the boxes because they're 2 different floors. And then this one has 2 in it, this one would have 1 in it. Now, as we keep going, I'm going to do 3 more examples with you, okay? If you're feeling good, as always, that's great, but you can't be talking to others until I've gotten through my examples, okay? All right, what is the next example? Thank you. Okay, so carbon, find it on your map. How many electrons does it have?
6.
So it's right there. Okay, where do I start? Always start here, which is 1s. How many can the 1s hold? Only 2. Okay, once again, if you're thinking through, it's like a board game maybe, right? Like, so I was here, and I went 1, 2. Now, I'm going to come here. What orbital is this? 2s. How many can it hold? 2. So I write 2s2. Here we go. Maybe we'll use one of my clamps as like our moving piece. Okay, so now we're here. Okay, I'm not to my magnet yet, so I got to keep going. What orbital is this? 2p. And how many spaces?
2.
1. 1s2, 2s2, 2p. Now, when I draw my orbitals, once again, we have our 1s,
When do we stop it? Okay.
we have our 2s, sorry, my boxes are
This
getting
is the
smaller.
X column, so I guess we have to fill out
Now, the
this X
2p
before we can get to that.
has to be drawn to scale, even if it's not full. So how big is the 2p? How many orbitals? Yes, you gotta draw all 3 orbitals connected, because that signifies they're the same sublevel. But then I only put 2 arrows in there, up, up. Because Hund's rule says spread them out with parallel space. Questions that haven't come to the brain yet? Okay, sodium, is that our next one?
Yep.
Okay, let's do sodium. Alright, find sodium on your map. Right there. Where do I have to start? 2s has
2.
2. 1, 2. Move across. This row is the
P.
what P?
2.
2p. And it can hold up to
3.
6.
so it has 3 orbitals, so how many
Oh.
electrons? 6. And the nice thing is if you forget, just count. 1, 2, 3, 4, 5, 6. Okay? Alright, I'm not to my magnet yet. So I gotta go down a row. This is the 3s. Got 3s. Okay. Try aluminum for a smiley face, okay? Ready, go.
It's right across
Fun little boxes. Good word.
Hey, confidence isn't bad. Yeah, but too much confidence is bad.
Yes.
Probably way too confident.
Okay, let's find it for uranium now.
The big ones, like, I can do it.
For uranium? Are you kidding me, Alex?
Yeah, it's just, typically if you write a real arrow, I don't care. But like, the chemist's way of showing an electron, they took like half an
No, let's not send uranium, please.
We actually use it in other ways too, that half arrow, but it is used like
You just gotta use a brain.
a lot. Another time where it's
Okay, so it
silent,
has. Hey, good start.
and then it's like completely different. Yeah.
So. Yeah, and then 2s. Then write it smaller. 3p6. And then this is where it gets complicated. No, wait, never mind. It's not complicated. Yeah. And then 4s.
No, it's just like math.
And then we get to this part.
Oh no, it's 14. Oh yeah.
Okay, I think I S-ed my way through and saw everybody's, but here's the answer. So if you didn't get it right and you don't know why, let's talk about it, okay? But you should have 1s2, 2s2, 2p6, 3s2, 3p1.
Yes, sir.
Questions so far? Now, what I'm hoping though is actually a lot of you have the question that Levi just asked me. Because that means you're like understanding where it's going, okay? Raise your hand if you feel confident with the skills I've taught you. I'm not saying you want to, but could you do this for OG?
Yes.
Yeah.
Oh, yeah. Yeah, it just be really long.
I just might not make it to the end.
I might die before I do
Yeah,
it.
I might mentally.
Mentally.
My mental health.
Okay, good. That's a good sign, okay? Because the longer ones shouldn't feel harder, they just feel longer. And tedious, there's a good word, Alex. So there is a way to shortcut this.
Yes.
Because scientists recognize the repetitiveness of it as well. And once again, the objective of what information matters. Okay? So now I taught you the long way because I wanted you to understand the process of how it all works. But now that you know the shortcut, you are allowed to always use the shortcut and you don't ever have to do the long way unless you're bored. Okay? The idea of the shortcut is to focus on the electrons that really
Still funny.
matter in terms of chemical reactivity. So we have things known as the valence electrons, and anything that's not valence is considered a core electron. The valence electrons are the ones in the outermost orbitals and energy levels, and they are the ones that result in bonding. They're the ones that trade or take or share the electrons. The core electrons, these inner ones, for the most part, they just orbit their lifelong through. And so that's the way the shortcut works, is by condensing all the core electrons into a symbol and then just listing the valence that comes after. Okay? All right, so let's do an example of how to shortcut.
I'm not.
Okay? All right, actually, I'm going to leave it on our book here.
Ha!
Okay, so our first one is manganese.
What if I already solved it? Yeah, I might I never marched very well.
Okay, so you do it over here, so Mn. Okay, so you start the same as you did before of finding where it is on the periodic table. So manganese is 1, 2, 3, 4, 5, right there. Okay. Now, the way the shortcut works is by using a select group of elements that are considered the most stable. And that is this column right here, the noble gas family. Okay? So, by using one of them, it consolidates it all into the core electrons. These are full, the energy levels are full. This is what isn't full. Okay? If you want to make a note on your map, you can only shortcut with these. That's the rule. Okay? You can't just make up your own shortcut. Okay, so it has to be something from this column. So if I want to do manganese, instead of having to start here, I'm going to use this noble gas because it's the closest to it, but still behind the pattern. So this is argon, I think, right?
Yeah.
Okay, so I'm going to put AR in brackets. Okay, this is the notation you have to use. This right here says 1 through 18 is good. So now I get to start here. So this section is 4S. 2 is 1, 2. And then this section is,
4D.
careful, 3D.
Oh, dang it.
4, 5.
Oh yeah, it's because it's stupid.
You know this is okay towards our atoms.
The electron.
But then you're done.
Periodic table.
If you're asked to do the orbital diagrams, yes, but you can shortcut the boxes as well, where you only draw. Okay. Yeah. Okay. So let's go back to this question that's been brought up a few times now.
That's cute.
So, and then I want to do another example with the shortcut here. Okay? So, the numbers off to the side, that period number, how do I put this, does represent the transition to a new energy level or shell. So every time you go down on the periodic table a row, you add a whole new ring or energy level to the atom.
Yeah.
What happens with the filling of it though is atoms fill, once again, we didn't make the atom, we're just discovering what the atom does. Okay? Once again, that's where this is also failing, is because the orbitals are not really like these solid racetrack things. They're much fuzzier clouded spaces with the ability to overlap, where there's actually overlap between the third and the fourth, particularly the 4s and the 3d. And so what scientists have found out is that because of that close overlap region, the atom always fills the 4s and then the 3d. So those 3d are technically part of the third energy level, but in the order of the filling, the 4s goes and then the 3d, because they're actually very close in energy value, I guess you could say. One thing that I hope as like a mnemonic to help me remember is the D is shifted down, right? So the D block is shifted down 1 from what it should be, and then actually the F block gets shifted down twice. So you'll notice that the 4F is lined up with the 6.
So that means that it did it.
Everyone see that? Okay. Another thing too, you could notice pattern-wise if it helps you, once again in remembering that, the S's start at 1, the P's start at 2, D starts at 3, and F starts at 4. Like there's no such thing as a 3F, that doesn't exist. No. Just like 1P doesn't exist. Those orbitals are too small to have more orbitals than that. So does that kind of make sense? Does it make it feel a little less stupid?
Yeah.
Okay. All right, let's do, what's the next one on our list for silver?
Silver.
Okay, let's do silver, and then I want to get down to the F block, just to see that one. Okay, so let's do silver as a shortcut, just to practice it. Okay, so AG is here. So shortcut choice would be this one. So KR, which means I'm going to start right there.
Yep.
So I'm on 5S, 5S2, 4D9. 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. And just like before, if you add up your exponents plus whatever's in the shortcut, it should add up to the total number of electrons. If you like to use that method to help you check. So, questions on the shortcut method or the D block, how that fits in? Okay, let's do LA to see how the F block fits into the pattern. Who would you pick to shortcut LA? Good, XC, right? Lower in number, but in that last column. Okay, so LA is here. Okay, I'm using this one. So start here. It's a 6S2. And then this is where hopefully you drew arrows on your map because people just sometimes forget about the F block. Right, so we go here and then we go down here.
Yes,
So
sir.
4F.
Yeah, we did it. Go.
Questions? Okay, some of you maybe already did uranium. If you did, I want to do a different last example for smiley face. If you did it, great. Good for you. But off to the side, or cross off uranium and change it.
No!
I want you to do gold. AU. Let's do a practice of doing rhyming configurations. Okay?
I want it.
Try that one for smiley face.
I was like a proud father staring at the sky when I stared at that cloud. But then you ruined it. We can't be friends anymore. Go to your best.
Yeah.
As a sport, you
Yes.
Because that one was it's 4. No, it's 5. 4. 4 out.
I did. Stop yelling like that.
Oh, yeah?
Did you tell him?
Yeah.
You're allowed to change your dress.
No, it's not.
Wait.
Oh, it's 5.
Both in the. Yeah. Oh, wait, no, you can say. Wait, what is that number?
There's a spacer block.
More letters.
Are you asking a question?
Oh, I always hear D.
I count 15. Oh wait, on that one. On that
You're a mom who likes You're a mom.
Yeah, so the number of the energy level does correlate directly.
I am so fond of servants
That's exactly how bonds work. It's like even though hydrogen only has an electron,
Dude, you dropped your pens. Yeah, excuse me. I dropped my pen.
Did I go get a drink of that? Thanks. Excited.
question. A few people already answered, but being that it was multiple times, some others may have that question as well. So you should have for your answer for, what are we doing? Goal? Yep, okay. XE in brackets. And then you should have done 6S2, 4F14, 5D9. So Jack caught on. So the reason why I picked gold is because often when you do an element past the F block, some students just forget about it and they just leave it out and they don't do the down and then the up. So keep that in mind. Okay? Any questions? That's why these are like, this is not this might make it worse if I show you because it's crazy. But I'll show you. So like the different orbitals, like the F, there's one called S, T, E, and F, they have different shapes. And the letter corresponds to the shape it has. So like S is the easiest, the others are like more complicated. Because S orbitals are all spherical. So 1s is always a sphere. The difference is a 1s is smaller, the 2s is farther away, and then 3s, right? But then the p orbitals and the other orbitals aren't spherical. A p orbital is shaped like this. Okay, so here's your nucleus in the middle. Okay, so that's its orbital path. And so then the reason why it has 3 options is because of you have a y, x, and z orbital. So all 3 together make up 1 p. And then a D is like this, but with 5 flower thingies, and then an F is 7. And so then you have to imagine like each of them individually, but then on top of each other. So like if you have carbon, you have the 1s, which is the sphere. You then have the 2s, which is a bigger sphere, but then you have the 2p on top of it as well. The orbitals are like the half. Yeah. Does that kind of make sense? Here's like a. Yeah. Just like used to show. Like so that's like the atoms. That's not what I was thinking. But that's only showing you like the most outside. There's like layers within it. And so then like if I go to like business, so like you can see like the dumbbell shape. Do you see how like yeah. So like so here's an S. Like the S's are like these. Like they just get bigger. So that kind of shows you like the core. That's why, like, how do I make that in models? So, like, this is why we teach you this in like elementary school, because that's just like what's good. It's like I think Yes, and it's not like this straight line, track that we sometimes see. They're much more fuzzy area. Like they occupy this space, they occupy this space. Yes, and then it's like on top of each other. It is cool. Okay, the last thing I want to end with today is there's some exceptions to the rules we just spent all time learning. Right? Now, the nice thing is you are not expected to like memorize an exception. For example, silver has an exception. We're going to focus on that one for our talk here. Okay? Okay? So this is what I would expect you to write for silver. Like if the question was, what's the electron configuration for silver? I expect you to write this because those are the rules. Through experimental methods, scientists proved or disproved this for silver, that silver actually doesn't do this. They found that silver does this. So write this on the line below. Maybe draw an arrow up to the other one to help you remember like the comparison. So they found that silver does 5s1, 4d10. Now once again, this is experimentally proven. Okay? Now, what you do need to be able to do in this class is if given an exception, like I say, hey, chromium has an exception. This is its actual electron configuration. Can you justify why it does it? Okay, so that's, don't think of like you have to memorize why the ones that do the exception, but if given one, can you provide a valid justification of why? So any thoughts on why silver would choose this over that? All on its own, right? It did it by itself. It moved an electron over. Dylan,
Have to do with like so they can all have their own bunk bed or own bed.
Ooh, that is a big part of it. So what Dylan said is he said it's something about them all wanting their own bed, and a big part is electron repulsion and what causes an atom to be stable, right? Atoms want to be as stable as they possibly can on their own. Often they end up bonding to become even more stable, but they want to be as stable as they can on their own. And so what we have found is the pattern, and so it tells us there must be some stability in this, is one of two options. Either a half-filled set. What we mean by half-filled is the S right now only has one. That's half-filled. There's a form of stability in being half-filled. The other thing that makes it stable is completely filled, especially large shells. So with this orientation, the D shell now, right, is completely full because it can only hold 10. When before, when it was 5s2, that one was filled, but 4d9 was like awkward, not there yet. That was my face to that, Dylan. Any other ideas of how I can know like when an exception might happen?
Well, I guess like basically like it steals the electron.
Steals, pushes, I don't know which way it comes from. I don't know if it gets pulled or pushed, but it transfers it to the other one. Yeah.
Just like make it happy and stuff, because with the original example, it was unbalanced and this was balanced.
Yeah. And the thing here is it's with the S and the D again. Because remember how we talked about that the S's and the D's are very close? That's what allows it to happen. If there's a big gap, the atom can't transfer the electron with added energy. Okay. All right. Homework tonight is just the 1.5 practicing electron configurations. You can use the shortcut every time now. You don't have to do the long one.
What about the AP classroom?
Off on the quizzes till next week. There's one last thing we need to cover that's on the quiz. It's like one question, but I don't want you to get to it.
For the 1.1 or either the 1.1 or the 1.2, there was a question that like we hadn't gone over yet.
Oh, on 1.2? Oh, thank you for